All right, our next lesson is on the valence shell electron pair repulsion theory. I think we're missing a word there. It says valence shell repulsion. Valence shell electron. Let's fix that. Yeah, that looks better. VSEPR. This has to do with the shape of molecules and polyatomic ions. Here's what it says. The geometric shape of a molecule or polyatomic ion is determined solely by the repulsions between valence electron pairs, whether these electron pairs are involved in bonding or not. So this is bonded or unbonded or lone pairs of electrons on the central atom. The repulsions cause the electron pairs to take positions as far away from each other as possible so as to minimize those repulsions. So there's 5 possibilities for the arrangements of the electron groups on the central atom. So I'm using electron groups. This can be, again, bonding pairs of electrons or lone pairs of electrons. And so I'm not going to distinguish between the two here. So if you have 2 electron groups on the central atom, the geometry of that molecule or polyatomic ion would be linear. And the furthest apart that those electron groups can get from each other in degrees would be 180 degrees. If you have 3 electron groups on the central atom, actually let's go back and draw a picture, and we'll use these diagrams a little bit later as well. Don't worry about the symbols right now, the A's and B's. Just know that you got 2 electron groups on the central atom, and the furthest they can get apart from each other is 180 degrees. This leads to a linear geometry. If you have 3 electron groups on the central atom, let's draw what that looks like. It looks something like that. The furthest apart that the electron groups can get from each other is 120 degrees. So in these examples, I'm showing just bonding electrons, but it could be a combination of bonds and lone pairs. If they're 120 degrees apart from each other, if there's 3 electron groups on the central atom, the geometry of this type of molecule or polyatomic ion is trigonal planar. 4 electron groups on the central atom. Let's draw that, see what it looks like. If there are 4 electron groups on the central atom, which could be 4 bonds, 3 bonds and 1 lone pair, 2 bonds and 2 lone pairs. Again, we're not distinguishing the difference, or in this case, 4 electron groups on the central atom. The geometry is tetrahedral. Be careful. I drew this 2-dimensionally, but molecules and polyatomic ions exist in 3-dimensional space. So it looks like the furthest apart that those electron groups can get from each other is 90 degrees. That would be true in 2D. But in 3D, they can get a little further apart from each other than 90. So we have a distance of 109.5 degrees. 5 electron groups on the central atom. Let's take a look at what that looks like. So again, this could be 5 bonds, or 4 bonds and 1 lone pair, or 3 bonds and 2 lone pairs. So 5 electron groups on the central atom. The geometry is trigonal bipyramidal this time. Here we have 2 different angles between adjacent groups. If you look in the textbook, I'll give you a page to reference when we talk about molecular geometries. We have 2 different angles to look at here, so let me show you. We have 3 going around the equator. I'm going to show those in a different color just to distinguish them. So those yellow bonds, yellow electron groups go around the equator. We call them equatorial positions. The distance between the equatorial positions is 120 degrees. And then the blue, those are known as the axial, A-X-I-A-L. The distance between axial and equatorial is 90 degrees. So again, let me add one more different color arrow so we can clearly see this. So there's what that looks like. All right, 6 electron groups around the central atom. Let's draw what that looks like as well. This time we have 4 equatorial electron groups shown in yellow, and then 2 axial shown in blue. This time the distance between each of them is 90 degrees. So unlike trigonal bipyramidal, the distance between each of the electron groups, whether we're comparing equatorial to equatorial or axial to equatorial, is going to be 90 degrees. Take a look on page 290, table 8.1. Go ahead and fix that in your notes. I believe it says table 4.1. This is table 8.1 on page 290. And especially with the trigonal bipyramidal and the octahedral, try to imagine those in 3 dimensions, either the kind of space-filling model on the left or the ball and stick model on the far right. It might be easier to see with the ball and stick model on the far right, just so you can get an idea of where the bond angles come from. Even the tetrahedral we can see is more than 90 degrees apart. And so try to imagine those 3D as those molecules and polyatomic ions or those geometries exist in 3-dimensional space. Last lesson, we talked about bond polarity, whether an individual covalent bond was polar or nonpolar. We can apply that same terminology to molecules. Molecules as a whole may be polar or nonpolar. So again, a polar molecule would be a molecule that has opposite ends. One end of the molecule has a partial positive charge, and one end of the molecule has a partial negative charge. If a molecule does not have opposite ends, then it is nonpolar. So let's take a look here. It says when a molecule contains 3 or more total atoms, so you got the central atom, and then in this case, our first example, 2 atoms bonded to the central atom, the arrangement of the polar bonds, as determined by the electron groups, must be considered in order to determine if the molecule has a dipole moment or not. So let me draw the Lewis structures for these 2 molecules. If you remember how to draw the Lewis structures for these, go ahead and pause the video and do those yourself. If not, you can just follow me. Pause the video if you want. All right, now let's do this. Let's indicate the polarity of each of the bonds in each of these molecules. Let's start with water. Of the 2, hydrogen and oxygen, which one is more electronegative? Oxygen is one of the most electronegative atoms, and so that means that the oxygen is going to pull the shared electrons away from the hydrogens. Let's show that. So also notice that in water we have that lone pair of electrons, 2 lone pairs of electrons on the oxygen end of this molecule. That, coupled with the oxygen being more electronegative, makes the oxygen end of this molecule partially negative. And because of that, the hydrogen end of this molecule is partially positive. Now let's compare that to carbon dioxide. So what these 2 molecules have in common is that they both have 2 atoms bonded to the central atom. However, they have a different number of electron groups, and that's what makes the difference between, in this case, polar and nonpolar. Still, though, let's take a look at the polarity of each of the bonds in carbon dioxide. Of the 2, carbon versus oxygen, which one is more electronegative? That, of course, would be oxygen. So let's show the polarity of these 2 bonds. So the oxygens pull the shared electrons away from the carbon. We end up with a molecule that does not have opposite ends. So carbon dioxide has no dipole moment. This is a nonpolar molecule. Next, let's compare these 2. What do sulfur trioxide and ammonia have in common just by looking at their chemical formulas? Both of these molecules have 3 atoms bonded to the central atom. So let's go ahead again and draw some Lewis structures. If you know how to do it for these, fine. If not, go ahead and copy me. You may want to wait on these ones because they're a little bit different. Just go ahead and pause the video if you want to draw them yourself. So for this example, I opted not to draw the lone pair of electrons on the oxygens in SO3. It's not important for what we're doing here. Also, the double bond in sulfur trioxide, not important, but I thought I'd throw it in there. All right, let's do the same thing here as we did in the last one. Starting with SO3, of the 2 atoms, sulfur and oxygen, which one is more electronegative? That would be oxygen. So let's show the polarity of each of the bonds in that molecule. So we see that we end up with a molecule that does not have opposite ends. The oxygens are pulling the shared electrons away from the sulfur equally in equal directions or opposite type directions. And so SO3 is nonpolar. How about ammonia? Of the two, which is more electronegative, hydrogen or nitrogen? Like oxygen, nitrogen is one of the most electronegative atoms. So here's what we get. And again, just like with water, we have that lone pair of electrons on the nitrogen end of that molecule. That, coupled with nitrogen being more electronegative than hydrogen, will give the nitrogen end of the molecule a partial negative charge. And because of that, the hydrogen end of the molecule is partially positive. So again, we see that due to the arrangement of the electron groups around the central atom, sometimes molecules are polar, sometimes they're nonpolar. Has to do with not just bonded atoms to the central atom. So in both cases, they have the same number of bonded atoms, but how those bonds were arranged around the central atom and the fact that there were some lone pairs of electrons on the central atom will make molecules polar. No lone pairs on the central atom and no opposite ends is going to make a molecule nonpolar. All right, that concludes this lesson. Next time we will look at the valence bond theory and see the relationship between the valence bond theory and the VSEPR theory and how they work together to determine the geometry of a molecule or polyatomic ion. Thanks for watching.